Chapter 11 about priority queue. Priority queue. We will go through this chapter, browse it really quick, skim it, and see what's special in it, and read the main headlines. Introduction. A priority queue is also known as a binary heap. Is a variant of queue. So it's a queue, all right? One of the types of a queue. Items are removed from the start of the queue. However, in a priority queue, the logical ordering of objects is determined by their priority. So we give priority. The highest priority item are at the front of the priority queue. When you add an item to priority queue, the new item can more to the front of the queue. Priority queue is very important data structure. Priority queue is used in various graph algorithms, such as Prim's algorithm, Dijkstra's algorithm. Priority queue is also used in the timer implementation, etc. Priority queue is implemented using a heap. A heap data structure is an array of elements that can be observed as a complete binary tree. The tree is completely filled on all levels except possibly the lowest. And heap satisfies the heap ordering priority. A heap is a complete binary tree, so the height of the tree with n nodes is always a function of the logarithm of the n. All right. Heap is not a sorted data structure and can be regarded as a partially ordered. As you can see from this picture here, 863. So this tree on the right hand side, is not fully ordered. It's not sorted. As you can see from the picture, there is no relationship among the nodes at any given level. So we have the 4 and the 1 here, even among the siblings. Heap is implemented using an array, and because heap is a complete binary tree, the left child of a parent at position x is the node that is found in position 2x in the array. Similarly, the right child of the parent at position 2x plus 1 in the array. To find the parent of any node in the heap, you can simply division. Given the index of y of a node, the parent of the parent index will be y divided by 2. All right, left and right. Types of heap. There are 2 types of heap, and the type depends on the ordering of the elements. The ordering can be done in 2 ways: min heap and max heap. The 2 types are min heap and max heap. Let's go through the first one, the max heap. Max heap, the value of each node is less than or equal to the value of its parent. So it goes down with the largest possible value at the root. So the root is the highest, max, right? And the other one is the opposite. Max heap operations, and here's the time complexity and all this stuff, right? The minimum heap or the min heap, the value of each node is greater than or equal to the value of its parent, so it goes in ascending orders, ascending. The minimum value at the root, so the minimum will be at the root. All right. Use it whenever you need quick access to the smallest, because the item will always be at the root. However, the remainder of the array is kept is kept partially sorted. Thus, instant access is only possible for the smallest item. And in the other type, instant access is always possible for the maximum output. Heap ADT operations. We have the binary heap creates a new empty binary heap. We have the insert to adding an element to the heap, delete max, delete the maximum element from the heap, find max, find the maximum is empty, return true if it's empty, size returns the number of elements in the heap, and build heap, build a new heap from the array elements. So create binary heap creates a new empty binary heap. Builds a new heap from an array of elements. We have an array and it builds it from an array. Here's an empty. All right. Operations, and each one of the table above is going to be described. Create a heap from an array, and here are the steps, 3 steps. And here's the graph given an array. Right. Just like that. Pretty interesting to go through, but don't want to make the video so long and boring. So just show these and move forward. And here's an example of a class called heap, and the private variables and methods, the public methods, right? Here's the rest of the methods, constructors. Initializing an empty heap can be done using this example here. The insert, or sometimes they call it enqueue, as opposite to the dequeue, right? To add something. All right. Here's the explanation. And here's the code, the C++ code. It's the add method. We have a value and we'd like to add it. All right. And the opposite of the add is the dequeue or the delete. And here are the 4 steps. And this is the table that shows the steps with the graph, and it's pretty interesting. And after that, we'll see the code. All right. And here's the remove code, C++ code, all right? And if we keep scrolling, we have the sort, and here are the steps, the 3 steps for the sort, heap sort, right? And of course, again with the steps on the explaining sketch here that shows the steps that about the sorting of the heap, which is a tree, a binary tree. All right. And it shows all the swaps and again and all this stuff. And here is the code that does that. Heap sort, right? Okay. And here's the analysis. And there is a note here. Let's go through it real quick. It says heap sort is not a stable sort and do not require any extra space for sorting list. So it stays it's not stable. Uses of heaps. Why do we need that heaps? Heap sort. One of the best sorting methods in place and log in time complexity in all scenarios. Selection algorithms, finding the minimum max, both for the min and max, median, and or even the kth largest element can be done in a linear time using heaps. Priority queues, heap implemented priority queues are used in graph algorithms. And we have two examples here. A heap is useful data structure when you need to remove the object with the highest priority, schedulers, timers. Graph algorithms, by using heaps as an internal traversal data structure, runtime will be reduced by polynomial order. Examples of such algorithm is the Prima's minimal. Because of the lack of pointers, the operations are faster than a binary tree. Also, some more complicated heaps, such as binomial, can be merged efficiently, which is not easy to do with a binary tree. So the heap, which is an ordered or prioritized tree, what are the so the heaps which are prioritized binary tree, they act faster. All right. Problems in heap. What are the cons? We saw the pros. What are the cons? We saw the benefits. What are the drawbacks? All right. So the kth smallest in a minimum heap. All right. The time complexity is high. The kth largest in maximum heap is also a problem. Takes time. 100 largest in a stream. There are billions of integers coming out of a stream. Some getInt function is providing integers one by one. How would you determine the largest 100 numbers? And here's a solution. Oh, so these are not the cons. Sorry about that. These are not the cons. These are like exercises, problems, and here's the solution. Here's the question, and here's its solution. And writing the code is like a homework for the reader. The kth largest in the max heap, here's the solution. All right. 100 largest in stream, here's the solution for it. So these are like questions and their solutions, or the roadmap of the solution, or the algorithm for the solution. It's not really a written code. Merge two heaps. To merge two heaps, we have these steps. To get the median function, we have the solution, right? And here we have the median code written. That's interesting. And here is minimum heap. Here's the code. Is maximum heap. Here's the code. And traversal and heap. Deleting arbitrary element from minimum heap. Deleting the kth element from the minimum heap. Print values and range in minimum heap. And we have the exercises of the chapter 11. And we have more exercises here. If we keep scrolling down, we have even more exercises. Then we have the next chapter, which will be in the next video, chapter 12, hash table.